Today we're going to do the notes for lesson 6.3, which is solve systems by substitution, where one of the variables is isolated. You can see at the top that the success criteria for today's notes is to be able to do this, to solve a system. And the examples that we're going to solve today use this new method called substitution. And substitution often involves using the distributive property to solve for one of the variables. So the launch in today's lesson includes two problems where you're solving for x and for y. Both of the equations just have one variable, and so you're solving using the distributive property. So you'll see here in example 1 that we start with the distributive property. So positive 2 times negative 5x gives us negative 10x, and then positive 2 times negative 3 gives us negative 6. On the left-hand side, we can combine the two like terms. So positive 4x take away 10x gives us negative 6x. And then we'll finish the equation by adding 6 to both sides and then dividing both sides by negative 6. So you get x equals negative 1 as the answer to that question. This is a multi-step equation that contains the distributive property, and so this is something that our class practiced back in Unit 2. The second example on the notes also involves the distributive property. This one starts using the distributive property. So positive 5 times negative 2y gives you negative 10y. And then positive 5 times positive 4 gives you positive 20. In the second step on this equation, you can combine the negative 10y with the positive 3y. That gives us negative 7y. And then we'll finish this equation by subtracting the 20 from both sides and dividing both sides by negative 7. And so for this one, we get y equals positive 3. Again, everybody, these examples were just a reminder about how to solve using the distributive property. This isn't the new skill that we're learning about today. We're going to practice that new skill when we get to the examples that are on the next page. So in the notes for 6.1, we practice solving systems using the method called graphing. And when you solve a system by graphing, you're trying to find the point where the two lines cross, but you're doing it by graphing both of the lines. Today's notes is going to look at the second out of 3 total methods that we use to solve systems of equations, and this one's with using a method called substitution. Using the substitution method is considered to be the easiest method when one of the equations has either an x or a y all by itself. And so if you look at the 6 examples that are down here on the bottom, the first 2 examples that are over there on the left side, neither one of them has an x or a y that's all by itself on its own side of the equal sign. So all of the x's and y's have coefficients. They have numbers that are in front of them. So there's no x or y that's already isolated, which means there's no x or y that's all by itself. If you look at these 4 examples that are over in the middle column and then the column that's over on the right, what all of them have in common is that one of the equations in each one of the systems has a letter that's all by itself, and it's been highlighted in yellow. So the first one has a y all by itself, so does the one underneath it. Even though it's on the right-hand side, it's still by itself. The column on the right, the x is all by itself in the top one, and then the y is all by itself in the bottom one. So notice that sometimes it's an x that's by itself, sometimes it's a y that's by itself. Sometimes both equations can have a variable all by themselves. And so when an equation is set up like this, it means that it's set up to be solved by substitution. Substitution may be the best method that you can use to solve these equations. The top side of the next page in the notes contains an example right here that's been solved by substitution. And we recommend that you use this T-chart or like this chart system to solve for substitution. So what you'll do is you'll start by writing one equation on the top part on the left column and one part in the top part on the right column. So one equation goes on either side. And then you're going to want to look at the equations and see which one has a letter that's all by itself. So in this problem, the y is all by itself. What we're doing is we're taking the x plus 1 that you see right here, and we're coming over and we're substituting it into the equation for where the y was equal in the previous step. So it's like we're taking out the y and we're plugging in the x plus 1. Once that equation has been substituted into the equation for the corresponding variable on the other side, you'll notice that the equation only has one kind of variable in it. So this equation just has x's. And so we can use algebra steps to solve to figure out what one of the variables is equal to. And then once we've done that, we'll take what we get for our answer for x and we'll plug it back in using the other side of the chart and we'll solve for y. The answer that we get to this question is the same answer that we would have gotten if we graphed the 2 lines. And so looking here, this is question number 5. I started the problem out the same way. So we write one equation on the left and one equation on the right. It doesn't matter which one goes on the left and which one goes on the right. You just want to put one on either side. And so here we're going to go really slowly through these steps. It's important that you see on this problem that we're starting by writing the things that are down on the left-hand side. So we notice that the x on the right is the letter that's all by itself, and its x is equal to 2y minus 6. So we're going to take the 2y minus 6 and we're going to plug it in for where x is on the other side of the t-chart. Once you've done that, you can do the distributive property. So 7 times 2y is 14y, and 7 times negative 6 gives you negative 42. And then in the next step, you can combine like terms. 14y take away 3y gives you 11y. And then finish by adding the 42 to both sides and dividing both sides by 11. So you get y equals 4. So all of that gets filled in on the left-hand side of the table first. Once you have y equals 4, then you can plug it into the other side of the table for the letter that it represents. So see here how I plugged the 2 in for the y, how I plugged the 4 in for the y. 2 times 4 is 8, and then 8 take away 6 is 2. So you get x equals 2 as the other part of your answer. When you write the answer to the question, you always want to make sure that you put the x first and the y second. It's an ordered pair. And that, again, is the point where the two lines cross. That's the solution to the system. So if we went through and did all the work and graphed these lines, we would also find that that's the point where the two lines cross. Example number 6, we're going to follow the same pattern. So we write one equation down on the top on the left, and we write one equation down on the top on the right. And so for this one, we're going to see that the y is all by itself. So our first step is going to be able to take that 3x and plug it into the other equation for where the y is. So it's like the variable is replacing the other letter. Once you have the 3x plugged in for the y, you can combine like terms. So negative 3x, take away 3x gives you negative 6x. And then we'll finish this equation by dividing both sides by negative 6. So negative 24 divided by negative 6 gives us positive 4. So the x value on this one is positive 4. And then we're going to plug that positive 4 in for x into the other equation. And so 3 times 4 gives us 12. And so the solution to this system, or the point where the two lines cross, is the point 4, 12. If we were going to graph these two lines, we could do the work and graph them, and that would be the point where the two lines cross. That we solve by substitution are going to follow this same pattern. So we're going to start by looking at the two equations, figure out which one of them has a variable that's all by itself, and then we're going to plug that into the other equation using this t-chart system. It is possible to do substitution without drawing the t-table, but the t-table is just a nice way to organize your work, so we suggest doing it that way. Sometimes when you're solving a system of equations, something funky kind of happens and the variables end up canceling out. And so we've seen this before when we've solved equations, but it looks a little bit different when you're solving a systems of equations, and it means something different when you're solving a system of equations. So if you're solving an equation and something kind of funky happens and the variables both cancel out and you only have numbers left over, you have to look and see if the equation that you have left over is either true or false. And so if it's false, it's no solution. And if it's true, it means infinitely many solutions. But this means something different than it did back when we solved equations in Unit 2. Look at example 7 to help us understand this. On this one, I start by writing one of the equations down on the left side of the table and one of the equations down on the right side of the table. This equation has an x that's all by itself, and so I'm going to plug the 7y, take away 5, in for x in the first equation. Have that step finished. My first step here is the distributive property. See how it's important that we practice the distributive property at the start of the notes today. So you guys, on this one, you're going to do 3 times 7y, so that gives you 21y. And then 3 times negative 5 gives you negative 15. But on this, when you combine the 21y and the negative 21y, the y's cancel. And so that didn't happen to us in the previous question. The equation that we have left over in this one is negative 15 equals negative 5, and that's not true because those two numbers aren't the same. And so when this happens, it means no solution, but because we're solving systems, we want to make sure that we remember that since we're trying to find the point where the two lines cross, what no solution actually means is that those lines are parallel. So the lines never cross each other, they never intersect each other. If we graphed this, we would see that the two lines were parallel to one another, and we could confirm by graphing that it's no solution. So substitution is letting us see that without actually having to graph the lines. Here in this final example today, we see the last thing that can happen. So I start by writing one equation down on the left and one equation down on the right. The y is all by itself on the equation on the right. So I'm going to substitute 4x minus 2 in for the y in the first equation. So we'll rewrite that and substitute 4x minus 2 in. Once you have the 4x minus 2 plugged in, you're going to start solving with the distributive property. Be careful with your signs on this one. So negative 4 times positive 4x gives us negative 16x. And then negative 4 times negative 2 gives us positive 8. And then in the next step, when you combine like terms, the 16x and the negative 16x cancel out with one another. And so you're left over with just 8 equals 8. And so in the last example, it was not the same number on both sides, but in this example it is. And so when that resulting equation is true, the solution is infinitely many solutions. But just like before, it means something different than it did when we solved one variable equations for x. When a solution to a system has infinitely many solutions, that means that the two lines are the same line, and so they overlap or they cross everywhere. And again, if we were going to graph these two lines, you would find that they're the same line. They'd be the ones with the double arrows on both sides, and they cross everywhere. Going back to the previous page, I just want to finish by saying that most of the systems that you solve are going to look like these ones, where you get an actual point that's an answer to the question. It's far more common to have a system like this than it is to have a system like on the next page, where you get either infinitely many solutions or no solution as your answer to the question. We make sure that the notes has a couple examples of each kind in them, but when you're working on the homework problems, it's more common that you're going to have ones that have a point as an answer to the question, as opposed to one of these special case scenarios. So good job, you guys. This is substitution. We're going to practice more of this in 6.4, but you're done for today.